Hey guys, I apologize for our first class being sort of remote or through this video. I'll try to make it up to you somehow. I don't know how, but Lord willing, I'll see you on Friday. So in class anyway. But here's a really exciting chapter to begin with. In a way, I do somewhat regret we didn't get to cover this chapter. I would have been a nice end to Organic Chemistry 1, but since we didn't get to cover it, our first chapter, starting off this semester, is going to be talking about organic synthesis. And as an organic chemist, or technically I'm more of a medicinal chemist, but organic chemist, this is probably the most exciting chapter in one sense because this is kind of why organic chemistry sort of exists, is to be able to build or make molecules of any kind. Whatever the science demands, whatever the medicine demands, we can build a molecule. And I want you to really think about that, like really complex structures of molecules that maybe, say, medicine demands or whatever. We could be like this atomic level engineer who could actually build such a thing using our chemical sciences. So I hope you see this as an exciting endeavor. And that's why organic chemistry is the central science to almost everything, because anything that you use in your life, whether it's your smartphone screen or the plastic material that you're using to do whatever with, even your clothes that you're wearing, all the drugs, and everything else that you might rely on, they are the result of organic chemists actually coming up with ways to build those molecules. And we, of course, understand biochemistry and everything else on the basis of organic chemistry. But anyway, here's some, just to elicit some appreciation, I hope. Here's some natural products, just to differentiate that word from like what you might see on Etsy, like essential oils. This just means secondary metabolites, as opposed to primary metabolites. After you're done with organic chemistry, many of you might go on to biochemistry. That's sort of the study of primary metabolites, and those are defined as nucleic acids like DNA, RNA, and carbohydrates and lipids, and proteins. But anything else is considered, anything else that organisms make are considered secondary metabolites. Those are often compounds that organisms make to defend themselves, especially those organisms that do not otherwise have defense mechanisms like plants or whatever, or even like things like sex pheromones. Those are considered secondary metabolites. But anyway, a lot of them tend to be bioactive, and so they make a great, and still to this day, the most important source of new drugs. I might actually say that here, that many And like I told you, organic chemistry really is the central science to all of pretty much everything. And the way that it developed was in large part due to chemists wanting to be able to produce or make molecules that are presented by nature. These natural products being synthetic targets. And here are some examples of natural products that have been synthesized here at Waynesburg University in our research lab, and or being synthesized as we speak. And these things often require modifications before they make it to the clinical usage, and sometimes also modifications are necessary so you can obtain an intellectual property, so you can patent it, or whatever, which you might think is kind of a bummer thing to do from your perspective, but let's face it, if nobody makes money off of drugs, no one is going to develop it or make it. That's just the reality of it all. So that's just sort of how that works. And so and a lot of these natural products might have promising activities, but sometimes they have some properties that do not make themselves the ideal drug. So you know, some things need to be changed a little bit. So these things often require, some modifications to the structures. And the only way to be able to modify these usually is through making them. So making the slightly different versions of these molecules. So synthesis is needed. We need to be able to come up with a strategy to make these molecules. Now, how do synthetic chemists come up with synthesis to like these complex molecules? Well, that's sort of what we want to learn. I want you to get good at, especially after this chapter. And you'll quickly notice, to be able to come up with a synthesis, you really need to understand chemistry or organic chemistry. And so everything that you learned last semester is very, very important still. Okay. So let's think about this. The way the synthesis scheme is usually conveyed. Here's the typical convention. I mean, the first part is probably no surprise to you. Typically on the left, you would have your starting material, right? That's not surprising, I hope. And and then on the right, you would have your product, right? And then on the arrow indicates that it's a reaction, of course, and then there's no really reason, but these reagents could be written over here on the left side of the arrow, but for what usually just to save space on paper, often a lot of the reagents are written either above or below the arrow. And here's some. This is the reagent. We said this is the starting material. And the product. And that's probably not surprising. And these are sort of the reaction conditions. Now, of course, this 80% is not a condition, but that was the experimental result. That is the percent yield from experiment. In other words, 80% of the molecules or moles of the study material was converted to this 1 iota butane, and then they were able to isolate that. That's what that means, okay? And of course, hopefully you can figure out what kind of reaction this is. This is a SN2 reaction, the iodide acting as a nucleophile. So I hope you can make sense of this, that sodium chloride is the byproduct, but this inorganic byproduct is often omitted. From the reaction equation, so that's why it's not shown there. Okay, so even though I wrote it here, I want you to know that that's not something most people would write down. Sometimes you see a reaction equation written like this, the second one here, okay? And in this case, it shows two distinct separate reactions. These are, this is very important because if you put potassium t-butoxide and bromine and water all together in the same pot, this reaction will not work. This is two separate reactions. They could have written this to show how the two steps are separate using two different arrows showing two different products, the products from the first step and then the product from the second step separately. But again, oftentimes just to save space, this is the convention. Now, when you see this, I want you to know that this is two separate reactions, okay? In other words, the product of the first reaction is often isolated. And the understanding is there's no carryover of the reagents. To the second step. Okay, so that's an important point. And in thinking about synthesis, often we talk about overall yield. This is easily understandable why we would be interested in calculating that, because let's say that the this is actually a sequence of synthesis. We started with chlorobutane, and then we made iodobutane, and then iodobutane was then converted to this bromohydrin compound in the end. So what was the overall yield for that above example from 1-chlorobutane to this 1-bromo-2-butanol? Final product. Well, the first step was 80%, and then the second step and the third step combined was 65% total. So those multiplied together, this is 52%. Oops. That's good. Over the 3 total steps. Right, the overall yield is important because if this final product is something that you're interested in, let's say as a pharmaceutical company, you'd be interested in knowing how efficiently you can produce that molecule. So this is your sort of the efficiency here. Okay. Now sometimes you have a little more complex situation, like molecule A. You use that to make molecule B, you use that to make molecule C, and then your end goal is to make molecule F, but to make that you need another fragment, molecule E. But this molecule E is not commercially available. In other words, you can't just go buy it, you have to make it from molecule D. And then let's say that each of these steps has these hypothetical yields, okay? Then what is the overall yield? This, by the way, is called a divergent synthesis. Because there's two different things I initially diverted, but they combined together to give you your final product here. Okay. When you're talking about, when you're looking at a divergent synthesis like this, as opposed to this was linear synthesis, what you do is you want to figure out the overall yield of the longest linear sequence. from 1-chlorobutane to 1-bromo-2-butanol, it was all linear, so that was the longest linear sequence. But the longest linear sequence here would be going from A to B to C to F, because that's 3 steps. But if you count from D, it's 2 steps. And the reason is that is you consider the longest part, because that's the hardest part, you know. That's the bottleneck, so to speak, right? So the overall yield of this divergence and synthesis is going to be 0.9 times 0.9, or 90% times 90% times 70%. So this is going to be 57% overall yield. Okay, so hopefully that makes sense. Usually if this was like an in-person class, I would ask you if you have any questions, but keep your questions, please ask me. You could email me if you want, but maybe even in class when I see you in person, or yeah, feel free to come see me as well. But if you have a question, it's possible a lot of other people have the same questions too. Now, so that's how synthesis is described, and that's great, but how do you come up with them? That's the hard part, right? You kind of need to organize the reactions you know in your head so that you could pull them out in a useful manner. That's kind of the key here. And almost all reactions that that you know, at least from this class, it's pretty much a reaction between electron-rich and electron-poor species. We kind of describe that normally as nucleophiles attacking electrophiles. That's pretty much how everything goes. Like, excuse me, that one sentence almost describes the entire year of organic chemistry. Okay, so here's a case in point. Hopefully you guys remember this reaction from last semester, from the alkyne chapter. Remember all the pi bond reactions, they are all electrophilic additions, electrophiles grabbing the pi electrons that are loosely held. That's the theme, right? So hopefully it's not too surprising to you to hear that 9-BBN, or the boron species, remember this is acting as the electrophile or the electron-poor species, while this alkyne with pi electrons to give is acting as the electron-rich partner in this reaction, right? And, and the end result is, hopefully you could figure out the product without looking at what I'm about to write here, but remember this would provide an aldehyde, right? Alkyne to aldehyde reaction. And if this seems foreign to you, I would really encourage you to go review this chapter from last semester. But what you see here is that this carbon here was electron rich, but now poor. Right, because electron-poor species reacted with this electron-rich compound. Why would I say that carbon is now electron-poor? Well, it's a part of a carbonyl group, double bonded to an electronegative oxygen. So that even has a partial positive charge. It's an electron-poor group now. But this we would consider as a functional group conversion reaction. Okay, we just wanted to go from alkyne to aldehyde. That's what we did. But the skeleton of the compound is still the same. I want you to note how we had 4 carbons in a row in the study material, and you still have 4 carbons in a row in the end. Now, another type of reaction category that I want you to be aware of, maybe this first one we might abbreviate it as FGC. The second one, CSA, or carbon skeleton altering reactions, goes like this, right? This is an example. Remember LDA, what it looks like? I hope you do, but the important part, not the lithium, but this is electron rich, isn't it? And the alkyne, you might say, well, you might say like, dude, isn't that the electron rich partner? Well, not compared to LDA. Compared to LDA, it does have like this electron pore part, which is the hydrogen, which has a somewhat of a small amount of partial positive charge because it's not as electronegative as carbon. So that you could say this is a little bit of electron pore. So the electron rich, electron pore reacts together to give you what? It gives you the LDA reacts as a base, pulls off the proton. So now the alkyne that was electron pore is now electron rich. You see the rhythm here? Electron poor things react with electron rich things, and you know, that's how everything goes, right? In the second reaction with bromomethane, right, there's a definite dipolar polarity, dipole moment in this molecule towards the halide. And so we could say that this carbon here is kind of an electron, poor species with an actual partial positive. And in fact, we would expect this alkynide anion to react in an SN2 manner. Because of that, electron-rich nucleophile attacks the electron-poor electrophile. And the end result is going to be that. And if we were to think backwards, if our goal is to make this compound, how would you know to synthesize this? Well, you just have to think about dissecting this, some bonds that you know how to make. Like that right there is a good bond to dissect, because you might know of a way to turn alkyne into an electron rich species like alkynide species, like right here. And you might know, if you're paying attention in OChem 1, know how to make this methyl group a good electron poor species by making it part of something like methyl halide, like that, right? So if you know that this two carbons can be poor, electron poor and an electron rich, then those two can come together like in this SN2 reaction we just looked at. So that's sort of in a nutshell the way you want to think about synthesis, okay? And you need to, like I said, have a good catalog of reactions. Here's just a review opportunities for you. I just pulled these from last year's or last semester's notes. So I'll let you review these, okay? But here I want you to work on these on your sort of on your own time. Of course, you have the answers, you know, back in the in your lecture notes. And one thing that last semester I really wanted to have covered, but like maybe we didn't have time for, is how to turn alcohol into a good leaving group by making it a tosylate. You might remember tosylate or a sulfonates being a great leaving group, and you might remember seeing tosylate group, which was often abbreviated like this, OTS, which is the same thing. Remember the structure, and you still do need to know the structure of these. Tosylate looks like that. Right, remember this is a great leaving group. and that's why you make them. But the way you do that is with a reagent called tosyl chloride and triethylamine. This is and it looks like that. So that's something I want you to know at this point. That just helps us with being able to come up with many different reactions. Well, excuse me, syntheses. And we briefly touched on this last semester, but kind of as a way of review, but to emphasize it and to even enhance it, the way you practically come up with a synthesis is you have to do retrosynthetic analysis. And remember, that meant that you don't go linearly from, you can't think forward in thinking about synthesis. You can't think forward from study material to come up with how to make the target molecule. You have to think backwards from synthetic targets. So if this is the synthesis target or the product that you want to make in the end, you need to think backwards. And I think we mentioned this, I can't remember, but this arrow specifically means retrosynthetic arrow, and this specifically means this type of arrow means that the synthetic target can be made from. So in this retrosynthetic scheme, again, the goal is to make this product, okay? If you think backwards, you could say, well, I know how to make that particular compound from this other thing, and then that other thing might still be an intermediate. On the other hand, you might be able to come up with a way to make the target from this some other compound, intermediate B. So we have thought backwards, right? You do that by, you start undoing the molecule, kind of by, we mentioned this, but this idea of dissection here. If we dissect that molecule, you might realize you could make that molecule from this terminal alkyne and a methyl bromide, right? Same thing, you undo the target, make it a little bit simpler, undo some bonds, and hopefully you can come up with starting material that you could make this target from. Okay, so this just needs to be at least slightly simpler. Of a molecule than the target. Okay, now by undoing this molecule, start. You have to start here, and then you have to start undoing. AKA dissection of the molecule. Okay. Now, usually, well, a lot of molecules, it takes more than one reaction to make it. So we established that we can make this target from these two molecules, A and B, but those may not be commercially available. We might still have to make these. So then you have to think about how these molecules could be made, right? It might take more than one step to make, but let's say this intermediate, you can think of a way that you can make it from this starting material A. Hallelujah. So then you could, and then this, let's say, is commercially available. Oops. And then that would complete a proposed synthesis. Maybe you could make this same synthetic intermediate from another starting material B, and you have that idea. That's great. If both of those are commercially available, then that makes for a good starting material, or at least a good candidate, right? And let's say this intermediate B could be made from starting material C, or it could also be made from starting material D, because there's usually more than one way to make a particular molecule. So what I'm trying to point out is you could make this target from many different starting material molecules. So if you're trying to think forward, there's just too many possibilities to begin your thinking from, and that's just an impossible thing to do. You have to have a starting point, and the starting point is the target, and since that's your final goal, you have to think backwards. It's kind of like, you know, I don't know if this is a very good analogy, but the first one that comes to my mind is if your goal is to have a, you know, happy, nice family, you and your spouse and, you know, 3 kids or something, then if that's your goal, usually you have to think backwards. You can't, well, I guess these days people have kids out of wedlock and stuff, but, you know, let's just assume that, you know, those things only happen in marriage. Then you first have, you can't just go get kids, right? You first have to think about getting married and then think about getting kids. But did you notice that in that thought process you thought backwards from the goal, right? The goal of this, like, two or 3 kids, nice happy family, but to get to there you have to be married first, but to be married you need to find a spouse first, so maybe you need to get out of your dorm room sometimes. So like that's sort of how the thought process goes. That's a retrosynthetic analysis. Okay. And I guess maybe we'll write this notes here. So how do you do that? Well, you sometimes you can have well, let's see. Maybe I do want you to have opportunity to maybe think about this synthesis. So maybe I'll stop the video here, and then I'll produce sort of the second one that you can watch, where I'll go through this synthesis. And what I want you to do here is I want you to think about the synthesis backwards, of course, from the target. And the way I drew the this retrosynthetic analysis arrow should make it obvious to you that this is the product, this is the target. We're not trying to make this alkyne molecule from that. We're trying to make this alcohol ketone molecule from the alkyne. Hopefully that makes sense. And in thinking about this, maybe I'll write that at least. This is the target. Sometimes you can think of a strategy, that synthetic route, that actually would not work in real life. And so I just want to showcase that there's more than one way that you could think of to make this. Some methods, some routes are better than others. So that's what we're going to discuss. And that's why I have 2 copies of the same thing here. We'll think about a couple of different routes. Okay. So see you in the next.